start recording. And let's take attendance. So please tell me that you exist. Thank you for being here. And let's see, is there anything else I need to say today? Nope, just the lecture. Cool. Let's keep on trucking. So we were on these slides for the non-programming lectures. We're actually going to do some programming today as well, though. So we're talking about game theory, talking about this cool prisoner's dilemma, which tells us why, apparently, if you're taken into two separate interrogation rooms, it's always better to confess. So that was fun. Let's keep talking about game theory. It's a fun little concept. Let's talk about cake cutting. So this is another game that you can play with somebody. Maybe you have played it before, like you're sharing something with somebody to eat, and you want to make sure it's fair. So you can define this in terms of game theory. And I'm not really sure. The internet, I looked it up. I can't tell if it's a cooperative game or a non-cooperative game to cut a cake perfectly in half and share it. Do you want to make alliances? Do you not want to make alliances? I think the issue is that that kind of cooperation is forced upon you. So maybe it really is non-cooperative. Who knows? So nobody could decide. But remember that a cooperative game means that making alliances is a good thing. That will lead you to victory. So yeah, here is the game of cake cutting. Somebody cuts the cake, right? One person gets the knife, they cut the cake, and then it's the other person who gets to choose, right, which piece of the cake that they want for themselves. So here's a cake. And maybe I get the knife, I get to cut it. It is always in my best interest, right, to cut it down the middle, because the other person is going to decide which piece that they would like. And I think that the person who is hungry, right, the other person, if they're hungry, they're going to want the bigger piece. And so it's best to cut it into two separate pieces. That's the idea. So the next person gets to choose. And that is the cake cutting problem, and that's the optimal strategy, right? If you want the most cake and you're the cake cutter, you better cut it directly in half. Because if you cut it in any other way, can you guys not talk while I'm talking, please? Thank you. If you cut it in any other way, then the other person's going to want to take most of the pieces, right? They're going to want this giant half. That is your loss, right? That's no fun. So you want to cut it optimally, if possible. And so let's talk about that idea of optimality. So in general, this problem is called a resource allocation. We are trying to take some resource, like a cake, and allocate it fairly to a bunch of people. And we would like that to be an optimal allocation. One definition of optimal is called Pareto Optimality, and that is perfect for this example. When you have your cake cutting problem, one cutting of it is called Pareto Optimal when, this is a bit weird, it's a long sentence, but it's going to make sense once I show an example. When changing the allocation always leaves somebody worse off. So for example, this cake cutting, even this one, where you cut it in a very weird way, that is that is in fact Pareto optimal, because if you change the allocation, for example, you cut a little bit more over here, somebody's always worse off. The other person, in this case, they're going to take a slightly bigger piece now when you change that allocation. Isn't that interesting? So no matter where you cut this cake, it's always Pareto optimal, you're cutting. Changing the allocation is always going to give somebody else more and somebody else less. That's kind of cool. So this is all about fairness. It's all about utility. So I think John Stuart Mill would be a big fan of Pareto Optimality if he was around when this came out. So let's talk about all the different ways to cut a cake in a Pareto optimal way. Which kinds of cuttings of the cake would leave someone worse off if you were to cut the cake a different way? Does anybody see something interesting about that idea, about that question? I have it in the next bullet. But no matter how, right? No matter how you cut this cake, it's always going to leave somebody else a little bit worse off, even if you cut it optimally. For our definition of optimal, even if you cut it like this, somebody's going to be worse off if you change that allocation, right? If you cut it a little bit more like this, somebody's going to be worse off. Somebody's going to get more and the other person's going to get less. So no matter how you cut the cake, even cutting the cake in half, or if you cut it in a weird way, every single kind of allocation, every single way that you could take your knife into that cake is Pareto optimal. That's really cool. That's an interesting problem that arises there, an interesting solution. And so now I can finally, now that we have this term under our belts, I can finally kind of explain to you why that prisoner's dilemma felt so weird, that solution felt so weird. Like, why should they both confess? Why was that optimal and why did that feel wrong? Well, it was because the Nash equilibrium, which we found last time, the Nash equilibrium was saying they're both going to confess. That was this state, right? The Nash equilibrium is not Pareto optimal. There is a way for confessing, right, that leaves everybody better off. That was this square. But that is not the equilibrium. That's not what the prisoners will choose, right? So that is why it feels so weird. Because I guess as humans, we like the idea of Pareto optimality. We have that in our minds. But the Nash equilibrium does not necessarily have to be Pareto optimal. And that is why we think this is so counterintuitive. At least that's why I think it's so counterintuitive. So that is a new definition in a nutshell, defined in terms of lovely large cakes and cutting them. Any questions about that? All right, so the next thing that I want to show you is how to be fair. Another way of being fair. Let's have an example of riding in a taxi or like an Uber or a Lyft. This is going to be a cooperative game because it makes the most sense for you to pair up with people and like share the bill. Yeah. So here's my fun example. We got two people sharing a taxi. Let's name them Alice and Bob. So here's my drawing of a taxi. Boop. And person A, person B, we'll call them Alice and Bob. They're going to get in the taxi, and here's the route that the taxi is going to take. So Alice lives on the way. So here's Alice's house. Alice lives on the way to Bob's house. Bob lives down here. Okay, so it makes sense for them to want to share a taxi. Now the question is, how much should each of them pay when they're taking the cab together? Okay, so let's say, let's make up these numbers. Let's say that if Alice got a taxi by herself, she would end up paying $5 for the whole ride. Okay, so the entire ride to get her home would be $5. But because Bob lives farther, if he went and got a taxi by himself, he'd end up paying $12. Yeah, so that's a bit longer. There's more traffic on the way home for him. When they both take a taxi, because Alice lives on the way, the fare at the end is still $12. Yeah. So now the question is, how do they split the bill? What's the fair splitting of the taxi bill? And so this is actually useful for real life. If you ever do this, I don't know if the Uber app's going to calculate this particular value for you, but now you know how. I'll show you. So the question is, how much should Alice pay in order to split that bill fairly? Okay. For example, we can't just divide the fare in half because that would be like Alice pays $6 and Bob pays $6. Alice was better off taking the cab by herself in that case. So that's definitely not fair. 6 and 6 is not fair. That's no fun. We have to figure out a better allocation, a more fair allocation. And the number that we're going to come up with is, if you look it up if you'd like to, it's called the Shapley value. That's this fancy number for how much Alice should pay that we're going to compute right now. So the way that you do it, the way that you come up with the optimal strategy or the optimal payment for both Alice and Bob is to think about this idea, the idea of permuting who's paying first and who's paying second. That's going to make a bit more sense once I give you this example all written out. But let me show you all the different orders in which people could pay. So Alice could pay first, and then Bob could pay second, or Bob could pay first, and then Alice could pay second. And let's use their original cab fare values. So if Alice pays first, she would end up paying $5, right? Because that would be where the cab places her. And then Bob would be getting the rest of the bill at that point. He'd pay $7. So that's one way to order these payments. Alternatively, if Bob pays his fare first and Alice pays the rest second, then Bob would end up paying $12 and Alice would end up paying $0 because the whole fare has been paid at that point. Okay? And so then we take that into consideration with somebody's perspective. So let's work from the perspective of Alice. So we want to figure out how much she should pay. So let me section this off, I guess. So here is Alice's cost in each case. If she pays first, she pays the full amount. So she's paying $5 to get her somewhere, to get her home. And then if she pays second and Bob pays first, she pays the rest always, then she ends up paying $0. And so the fancy number that is the fare for this definition of fare, price, is going to be the average across all these different orders, all these different orderings, these permutations is the fancy term. All right? So if we calculate the average of how much Alice would pay across all these different orderings, we end up with $250. And this is, in fact, the optimal, for a certain definition of optimal, this is the optimal bill to give her. So Alice should pay $250 for the bill, and Bob should pay, I guess, $9.50. So they both save money, and this is the optimal way. Okay? So it's better than 6 and 6. 5 and 7 is, of course, still not fair because then Alice is paying the full amount. This is the optimal amount, $250. Are there any questions about that? It's called the Shapley value, and that's how you compute it. So next time you're taking a cab with somebody and you're just asking them to Venmo you something, this is how you calculate what they should pay to you. It gets a bit weird when you have 3 people in the car, because then you have a bunch of different orderings of who pays first, who pays the remaining amount, and so on and so forth. But this is the way to do it. All right, we all still doing okay? My last example for these slides is fun. It has to do with Tic-Tac-Toe, which I assume we all know how to play. So, my final example, this is a game, right? Tic-Tac-Toe. There are ways to always win it, right? Or at least tie. Assuming you go first, I think there's always a way to either win or tie. Not sure about going second. It's been too long since I've researched this. But I'm going to teach you a fun algorithm now. It's called Minimax. And it's a way to find the optimal strategy to play a certain game. But we're going to consider Tic-Tac-Toe. So here is a game board. Let's say that the game is in this state right now. We're playing with our friend. And X goes first. So X made the first move, which means that it's X's turn right now, since there are 6 marks. So X should go next. And what we would like to do is figure out what is the next best move for X to play. Obviously, I think we can all see the right answer, but we can train a computer, we can teach a computer to think in this way and always see the correct answer, even if it's not as obvious as this case. Okay? So the way to do this, no matter the game board, figure out the next best move is to simulate the entire rest of the game. There's not a lot of different options in Tic-Tac-Toe, right? It's either the first square is an X and O or a blank, the second square is an X and O or a blank, the third square is an X or an O or a blank. And so there's 3 to the 9th power possible game boards. We can store all of those in a computer. That's not too many. So that is how we're going to do it. Let's just enumerate all the different moves from this point onwards and see what happens and who wins. Okay? So the way that you can play this, the optimal way, is called Minimax. So the reason it's called that is because it's there's some min parts of the game and then there's some max parts of the game. So let's pretend that we are X and we would like to win. So when it's our turn, we want to make the move that maximizes our chance of winning, right? Because that'll give us the best chance of winning. We want to maximize our chances. And then also, we have to simulate the game, so we have to also simulate how our opponent is going to play, right? When it's our opponent's turn and we have to think of a guess for them, we're going to assume that they're going to make the move that minimizes our chance of winning. Like they're a really good player. They're going to make sure that we can't get as much as we want, right? They're always going to make the best move. So we want to maximize our chance of winning. Our opponent wants to minimize our chance of winning. And if we assign numerical values to each game state, we can find the best one. We can see what should have happened, how we should play this game, okay? So the idea is, like, here we are, we're in this state. What are all the different ways that the game could unfold from this place? Like maybe we could make a move that makes the game board look like this, and then we can make another move that makes the game board look like this. And there's a bunch of different moves, right? All along here, tons of them. And they all unfold, they go very deep. And that is what we need to do inside of a computer. We would like to enumerate all of these different moves. And there's a way to do that, okay? So I want to teach you how. Let me have you try this first bit of the algorithm yourself. I would like you to enumerate all the possible moves from this point onwards, okay? And I'll do one for you. But here is our game state. Here is our board, okay? Starting here, I would like you to make a chart that kind of looks like this of all the different next moves that you can make. You don't have to fill it in all the way down, but at least fill in the next row, yeah? So assume that it's X's turn. Make a chart of all the different ways that X could move. So, for example, here's one move for X. I'll fill in the first one for you. So here's our current state. So it's X, O, 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 X, X. X could go here next, right? That's an open spot. So that's a possible move from there. And then I want you to fill in all the rest. So try all these. And if you have time, if you feel like it, also fill in, like, okay, now it's O's move from this state, right? You always trade off, or all the different moves that O could make. So for example, X, O, O, X, O, X, X, that's the original board. O could move here. That's the next move. That could be like that. So that was the next move. I'll try to make it bold. That was the next move. Do you see what I'm trying to do here? You see how I can create that? So give that a try. Take a few minutes, help out your partner, and see if you can make, at least for X, enumerate all the different moves, and try to go as deep as possible if you can. And this is going to tell us something about which moves we should make next. Okay, I'll teach you how to play the Minimax game after we have this the state space. That's the technical term. The state space once it's enumerated. Okay, so give this a try. I'll give you a couple minutes, and then we'll come back, and I will teach you Minimax. All right, that is my timer. Were there any questions that came up while we were trying that? Did it make enough sense? So along this route, like this is X's moves, and only X gets to move next, right? Can't have some extra O's in there. Let me show you how to do it. So starting from this game board, let me enumerate everything for you now, and I'll teach you Minimax. So if you have the time, this is how you can win at Tic-Tac-Toe, but it's always better to write a program, that's for sure. So here's the first move, OXX. Let's just confirm that was the right one. Yes. All right, so now let's think of all the different places that X could move to. It's either like right here, or right here, yeah? So those are the next moves. There's 3 possible next moves for X. These 3. You know what, if I was smart, I would copy that. Let's see if I can. Oh yeah. Boop. Boop. That is peak efficiency. All right, so then X could move here. Nope. I gotta go back to the pen. X could move here. Eventually it's going to work. X could move here, or here, right? I think, yeah, that's perfect. That's the ordering that I wanted. And then it's O's turn, yeah? So it's O's turn anywhere that they could possibly make a move. So there's 2 spots that O could go in, here or here. So there's going to be 2 little sub-game boards below this one. And then there's also 2 moves for O below here. 2 little sub-game boards below that one. There is no game after this one, right, in the middle, because that game is over, yeah? X is won. You can't move anymore after somebody's won the game. So that's a win for X. We're good there. And then let's think of these other ways. So O can move here. Oops. Or here. Back to the pen. So O could go here or here. And then we have one more over here. Honestly, it might just be faster for me to draw out the board. So it's XOO, OX, XX, XOO, OX, XX. And then just quickly, let's see here. O won this one. There's no moves after this one right here on the left. So that game's over. X gets to win like kind of twice now for this game board though. There's only one move that X could make here, and it's a winning move. X, 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 along, like making L out of X's kind of. Good for you, X. So that'll win for X. And then there's also, let's see here. I need to move for O here, don't I still? So O could have gone here or here. So again, we have a win for O, like this along the diagonal. And then that last move for X is going to be a winning move right here for this other option. So it's going to be X, O, 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 X, and then X, X, X. So that's how we end all of these games. So I have now enumerated all the possibilities up until the ending point. Turns out there's always going to be a winner one way or the other, which is nice. Sometimes it'll be a tie, but it looks like there's always going to be a winner here. And so now that we've enumerated this, we've seen how the different ways you could win would be. Now we do what's called Minimax. So we maximize, boop, boop, boop. We maximize our chance of winning, pretending we're X, and then we assume that O, when they get to go, is going to minimize our chance of winning and maximize their own. So minimization, maximization involves numbers. So the first step is assigning a number to every game board, okay? So let's do it from our perspective. We're X. Let's say that every time we win, we have a state where we win, that's +1. We're going to assign the number +1 to that board. So +1 here, +1 here, +1 here. And then every time O wins, that's bad for us. So that's going to be a -1. It's going to be a score of -1. We don't like that board. -1, -1. Okay? And then the idea is you do this for the end games, and then you propagate up numbers based on Minimax, the Minimax rules. So for example, here, right here, what should be the score for this game state? Well, it always leads to a win for X. We want to maximize our win because it's our move right now. So this will be a +1. Likewise, over here, this will also be a +1 for the same reason. Okay? And then we go up here. This is now O's turn, right? And we assume that they're the best player ever. They're going to do the right thing always and try and guarantee a win for them. So that means they're going to try and minimize our chance of winning. You see that? So now, given these two options, like let's say we want to assign a score to this particular board, we consider this option 1 and this option 2. O is going to try and minimize our score. So they're obviously going to go for the win there. And so we should assign the number -1 to this move up here. Does that make sense to us, how I'm doing that and propagating those numbers upwards? It always flip-flops every time you make a move, because it's either X's turn or O's turn. And so again, likewise, for this move, what number do we assign? It's going to be O's turn, so they're going to minimize our chance of winning. So they're going to take the smallest number of the options. They're going to take the -1. And now we flip-flop. It's our turn. We would like to, it's X again, we would like to maximize our chance of winning. So what should be the number that I give to this state? Can we guarantee our victory for X? Yes, we can. Yeah, so we're going to maximize our scores of all these options. The score for this particular state is +1 because we can win. This is what Minimax is going to say from this state now. We've enumerated all the possibilities. Minimax will say, okay, this is your move X. This is the best move for you. And I hope you have some intuition now why. And so you can do this for any game state, even the initial state, though you don't have much information there. But you can play this kind of game and get down to the ending states and propagate back upwards those scores. And that will always tell you, as long as you keep flip-flopping, taking the Minimax properly, the correct next move, depending on the player. And you can always flip this idea where you do it from O's perspective and assume that +1 is good if, like, maybe you're O when you're playing or something. But this is how you do it. Are there any questions about Minimax? That's a fun little nice combination of an algorithm plus game theory. All right, so I have a little bit of another set of slides for us, and that'll be it. I want to talk about recursion and beauty, and I think we only have time for recursion because of all the holidays we had in this class. So that's quite sad, but we're going to get through it together. Okay, so let's talk about recursion first. What is the idea of recursion? If you've never heard this term before, it's about you have a problem, you're trying to solve it, and you're trying to solve that problem in terms of itself, which is really weird to think about. Like, I'm trying to solve for the factorial of a number in terms of the factorial of a number. That seems weird. So it might sound like it's circular reasoning to want to do this, right? We know that's a fallacy that'll never lead you anywhere. Like, you keep going around in circles. Do you ever solve the problem? Isn't that circular reasoning? And the answer is no. I would not be trying to teach this to you if it didn't lead us anywhere. The reason why it's no is because of these pictures. So let me go to this slide for a second. I'll come back. So the idea is, as long as the problem you're trying to solve gets smaller every time you try and find itself inside of itself, then it's going to lead you to the answer. Like, so these, like, Russian stacking dolls, for example, they get smaller and smaller and smaller, and they have a smallest version. If you've ever played this game, you can only move smaller pieces on top of larger pieces, and you have a smaller stack to work with. So you can think of it that way. And as long as you have smaller problems within your original problem, and you solve just those, you really can solve a problem in terms of itself. It's like, here's your big problem. You find a version of that problem inside of itself, and you use that to solve the original bigger problem, and it all works out. So let me show this to you. It's very fun if you haven't seen it before. If you've taken a programming class, you've definitely seen it, but I'm going to try and give you at least a little bit more intuition. At least you'll have seen it again. So let's do this. So solving a problem in terms of smaller versions of itself is really what recursion is about. So here is your game plan. If I ever give you a recursive problem to solve, here's what you do. You notice where that problem exists inside of itself. That's kind of the hardest part most of the time. And so I'm going to give you one good example today, and that should help you if you ever get a problem like this in the future. And that smaller problem, just terminology, we call that the subproblem. And find that same problem inside of itself, we call that a subproblem. Okay? And then finally, we think of a nice way to answer our original problem using that subproblem's answer. So you use the answer to that subproblem to solve that largest original problem. All right? And so all of this probably sounds really vague if you've never heard of this term before. And so the best way to explain it really is an example. So let me give you that example now. And I want you to try it. So I claim that finding the factorial of a number is a recursive problem. And I want you to try an example. So write out, we all know what 5 factorial is, by the way, right? It's 5 times 4 times 3 times 2 times 1. We all know about factorials, right? So taking a factorial, do that for 5, for example. Can you find the smaller factorial inside of 5 factorial? Take like 2 minutes to try it and show your partners if you think of it. Okay? So write it out. Where is a smaller factorial inside of 5 factorial? Where is a smaller factorial inside of 10 factorial? So think about this. See if you can write an equation that looks something like this. Okay? And then I'll show you what I'm thinking. Take a few more seconds to try this, and then our next goal is to generalize this idea. Whatever we just found, we want to generalize that to work for any number. All right, that was my timer. So here is 5 factorial. 5 times 4 times 3 times 2 times 1, right? So where's a smaller factorial? Did we find one? Where is it? Yeah, I see 4 factorial. Is that the only answer? Yeah, there's more than that. There's 3 factorial sitting right here, right? 3 factorial. There's 2 factorial sitting right here. There's 1 factorial sitting right here all alone. 1 factorial. There's a ton of smaller factorials inside of the original factorial. Isn't that weird? Did we ever notice that before? If you weren't shown this problem already. That is. So that is what it means to be a recursive problem. We can find smaller versions of the problem we're trying to solve within a bigger one. That is odd. But that will lead us to an interesting way of solving it. All right? So we found that smaller factorial inside of 5 factorial, and this works for any size, right? So 5 factorial, yeah, it equals 5 times 4 times 3 times 2 times 1. And here's 4 factorial. Usually for recursive problems, you want to find the next smallest factorial, the next smallest problem. So 4 factorial is the one to look for in 5 factorial. And that means we can rewrite 5 factorial as what? 5 factorial is equal to 5 times 4 factorial. That's weird. That's cool. And so this is a smaller factorial problem. If you write it this way, a smaller, I guess, factorial finding problem. AKA a subproblem. And so this works for any factorial that's bigger than 1, right? So like 7 factorial, that's equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. This totally generalizes. There's 6 factorial sitting right there. So taking these 2 examples for a ride, what do we notice? How can we generalize this idea that 5 factorial is equal to 5 times 4 factorial and 7 factorial is equal to 7 times 6 factorial? What does that tell us about how to calculate n factorial for some number n? Because that's where we need to go with this. N factorial is following these 2 patterns. Well, 5 factorial is equal to 5 times 4 factorial, so n factorial is equal to n times, this is n factorial equals n times, this is n minus 1 factorial, isn't it? So this is the generalized solution. N factorial equals n times n minus 1 factorial. And that tells us how to solve the original factorial problem, a bigger one, in terms of smaller versions of itself. And so this is called the recursive case of the solution. The recursive case. This does not give us the final answer, though, because if we keep unfolding our problem in terms of this, we'll never get to an answer. Let me show that to you. So we also need what's called a stopping condition or a base case. And that tells us when, like, we don't have to use n minus 1 factorial anymore. When can we just stop when we finally know the answer originally? Okay, so here is one way of noticing that. So if I take my 5 factorial and I unfold it according to this definition, plug in 5 for n, 5 factorial is equal to 5 times 4 factorial, right? According to this definition, so 5 times 4 factorial. But what is 4 factorial but 4 times 3 factorial according to this definition? But what is 3 factorial? According to our definition, it's just 3 times 2 factorial. And 2 factorial is equal to 2 times 1 factorial. And then 1 factorial is equal to 1 times 0 factorial. We keep on unfolding it. Technically, that 0 factorial is defined to be 1 in math. That totally still works. But then if you unfold it according to the definition one more time, what is 0 factorial but 0 times negative 1 factorial? Those don't really exist. And this will actually force the final answer to be 0. So we definitely don't want to go this far, right? I think we can also just not go this far either. I think whenever we see 1 factorial, that's a good stopping condition, right? If we ever see 1 factorial, just say that the answer is 1. Let's not worry about calculating 0 factorial and multiplying it by 1 and following this recursive case rule, yeah? That is our base case. Hey man, if you ever see 1 factorial, if somebody's asking you for that, just give back 1 as the answer. We're done. Call it a day. There's no need to run the recursive case rule. So these 2 equations become the final recursive solution. So you have your recursive case and your base case, which tells you when to stop, when you don't have to do the recursive case anymore. Okay? So if you unfold your original 5 factorial according to these rules, you will end up with the correct answer, won't you? Isn't that neat? So this leads us to a way of programming this. We can program these two equations and end up with a solution that gives us the answer in a very weird way. It doesn't involve a loop. It kind of loops using function calls. Let's talk about that. Let's write a function that computes this factorial, okay? Because usually when you're solving a problem in computer science, you're going to write a function to give you back the answer. And a function that is recursive means that it needs to ask itself for answers to smaller problems, right? So that means a recursive function is a function that calls itself on smaller inputs inside its body. That's really interesting. So fact, if I call it fact instead of like exclamation point, like the name of the function that compute the factorial, if I call that fact, I can ask for, hey, what's fact of 5, Python? And then according to our definition, it will take fact of 5 and multiply it by fact of 4, right? So it needs to go off and ask for the factorial of 4. It's going to call itself. Isn't that neat? So let's code this up. Let me show you how this works. Oops. I have no idea why that's having an error. Try again. Maybe it didn't. Maybe I lost the connection to the internet. That's probably what just happened. Well, that's no fun. Is it going to keep doing that? We'll find out. So let's make a function now called fact. I'll write it on the screen just for now, and then we'll code it up in Python. So def fact. I cannot write and talk at the same time, apparently. Def fact, and it's going to take some number n. What is the number that I want to compute the factorial of? And so we would like to give back, right? This function needs to compute n factorial. Yes, computes n factorial. What do we need to give back now? So we are inside the factorial body now. We're running the function. We got some n. We need to figure out what to do with that n. And so the first step is figure out, are we in the recursive case or are we in the base case? The base case is when our n that we're asking for the factorial of is 1. Otherwise, we say it's n factorial. Okay, we run this other rule with that generalized n factorial. But if somebody gave us 1, then just give back 1. So there needs to be an if else. Okay, if the number we're trying to compute the factorial of, if n, if that's equal to just 1, then the answer is immediately just 1. This is our base case. Base case, return, 1 is the answer, right? That is exactly this rule right here. This 1 factorial equals 1. Let's see if I can fix my internet, or at least just turn it off, because that is not very fun. Connect. You can do it, little guy. That's better. All right, try again. Leave me alone. Okay, so that's our base case. We just programmed this one. Now, if we're not in our base case, we're in this recursive case, this generalized case. In that case, else, what do we need to give back? Well, we need to give back our original n times n minus 1 factorial. And this is where you like believe in the magic of recursion. You just throw off the answer to yourself, but a smaller version of yourself. So you go off and compute, okay, let's call it x. What is the factorial of n minus 1? You go off and ask yourself, right? You're calling yourself within yourself right now, which should make you feel uneasy, but it will work. And then you return, what's the final answer then? Assuming you were able to compute this, that is the factorial of n minus 1. You were asked for the factorial of n though, right? So we're following our recursive rule. We need to give back n times the factorial of n minus 1. So, because I saved it off into x, I need to return n times x. And this is where the magic happens. We call ourselves for a smaller version of the problem. And this will eventually get us down to the base case, give back an answer, and keep on running this rule a bunch of times. So let me blow your mind by coding this up and showing you that this is a function that always gives back the right answer as long as you don't give it 0 or any number less than 0 of the factorial of any n. Okay? Let me show this to you. We'll compute our fact of 5 for real. So this needs to be saved where? We are in lecture 29. Well, let me make a folder for us for that. Beautiful. There, and let's call it fact.py. And let's implement what we just thought of. Here's how you compute the factorial of any number. Def fact of n. This is going to give back the factorial of the number n. We have to figure out if we're in our base case or if we're in our recursive case. So if n is 1, the rule is, for the base case, to return, the answer is just 1. If you're asking for the factorial of 1, if n is 1. Otherwise, we're going to save off the factorial of n minus 1. We're going to call ourselves. This is the recursive case. I should put this in also the slide as well. Recursive case. That's hard to read. Let's go back to blue. So this is the recursive case. The answer is n times n minus 1 factorial. But we've gone off and saved n minus 1 factorial. We've called ourselves. Somehow we've done work, and we put the answer into x. And so if we return n times x, that is the final answer. So in either of the cases, we're giving back some answer. After doing some smaller work, we're calling ourselves. And this will work no matter the n. So print fact of 5. Let's watch this happen. Run module. Fact of 5 is apparently 120. It computed 120, but what is the right answer? 5 times 4 times 3 times 2 times 1? Oh man, it's 120. So this weird looking function, there's no loop anywhere. You'd think that it needs to loop from 5 to 4 to 3 to 2 to 1 to multiply them all together. There's no looping that is obvious, and yet we are calculating the factorial of any number. Are there any questions about this idea? What we just did. Isn't that cool? So, let's see. We were able to do this. We were able to say print factorial of any number. 5 works. 7 works. The answer is 120 for 5 at least. It works for everybody. Print fact of 5, print fact of, 3. That's just 6, right? It's always going to give back the right answer. And let me try to, because I think this is the last non-review lecture, let me try to show you why. And I need to teach you about what's going on this thing called the stack. Okay? So this is going to bring it full circle to teach you exactly why this is doing what it's doing. But let me, I have to show you something called the stack first. So think of this diagram that I'm about to draw as a stack, like a bunch of papers, a stack of work to be done. And it also, depending on who's on top of who, it also shows in this diagram who needs the answer from the next person. So also who wants whose answer, which will become apparent when I give you the diagram. Okay, so originally our code was like this. We defined the factorial function like we started out with no work to do, and then we put on some work for Python to do for us. So I'm going to draw this as like a piece of paper that I'm plopping onto the desk. I asked for print of fact of 5, please. And this is going to make it be finally apparent why this factorial function does what it does. Why this actually gives back the final answer correctly. So I'm asking for print of fact of 5, and then, well, print needs the answer. It needs a number, like fact of 5. Yeah, that's not very useful for me. I need to go off and compute the answer to fact of 5 now. before I can print that thing. So there's some more work to be put onto the table on top of this one. So do this first, Python says. Do just fact of 5, please. And so now we can see who wants whose work done, right? So fact of 5, we're doing that because the person below it asked for it. Print of fact of 5 needed fact of 5, so we can actually give back some number to print. Okay? So we're getting fact of 5. Now we're off and we're computing it. So now we're in this code where n is 5. All right? And so that's not 1. It's going to go here. It's going to try and compute in the x variable. The x variable lives here. It's part of the fact function call. It's going to try and fill this x variable with fact of n minus 1, which is 4, right? The factorial of 4. And we need that number to continue and actually return a value. So look what happens. Fact of 5 is going to put some more work onto the table to be done. I can't finish until somebody tells me what fact of 4 is. And so this is called a stack diagram for this reason, like you're stacking a bunch of work that is still yet to be finished. And so fact of 5 is not done. It's still waiting so that it can give back an answer to print. It goes off and it throws some work on the shoulders of fact of 4. Okay? So I have 2 calls to the same function right now. And that is the key. I'm going to have a lot more where that came from. Okay, so fact of 4 is going to compute something because fact of 5 is waiting for him. Okay, and fact of 5 still needs to compute something because print is waiting for him. All right, that's the idea. And so fact of 4, now it runs the same function again, but now n is 4. Now n is 4, and we hit the else case. And it has its own version of the next variable. It's got its own little x, a separate one, that it needs to fill with fact of n minus 1, but n is 4, which means we need 3. We need fact of 3 to be called now before fact of 4 can return something. So it needs to throw off some work, place some more work on the table, ask for fact of 3, please. Are there any questions about what's happening right now? This is definitely very subtle. There are a bunch of calls to the same function, and they're all sitting right here. They're all sitting on this line. They all have their own version of n. They all have their own version of x because they're trying to compute separate things, the factorial of 5, 4, and 3. None of them are finished yet. There's still work on the table to be done. Yeah? Are we all good? Please yell at me if not. But again, we have fact of 3 being called, so now n is 3 for it, and again, it's not the base case, so we're going to be here. Again, x equals fact of n minus 1. So it has its own little x, and it needs to fill that with factorial of n minus 1, but its n is 3, so it needs to go off and call factorial of 2 before it can finally give back an answer to the person who needed it, which was the person below it, factorial of 4. All right, so fact of 2 needs to be called now. And again, we're going to hit the recursive case because n for that call is still not 1. It needs to set x to be fact of n minus 1. N is 2 here, so it's going to go off and call fact of 1. I need that answer before I can finish my work and give back my result to the person below me on this thing I'm calling the stack. Okay? Stack of work to be done. So finally, this goes off and calls fact of 1. All of these calls to fact have yet to return. They're still waiting on somebody. They're still waiting on work to be done by the person above them. And finally, we call fact of 1. So n is finally 1 for this particular call to factorial. And then we're here, we're in the base case, and we can return 1 immediately to whoever asked us for this answer. And the person who asked us was the person below us on this stack of papers, on the stack of work to be done. So fact of 1 returns 1 to fact of 2, who is waiting on this line for that answer. Does that make sense to us? That is key. That's going to allow us to unwind all this and get back at the final result. So fact of 1 is now done. My work is done. Take it off the stack. So now we're back. I should really erase this, but I'm going to keep it here for posterity. Now we're back in fact of 2, who finally got back an answer from fact of 1 to put into its x variable. So it's going to put a nice 1 right there. It's like, okay, cool. I'm done with this line now. I can now go on to this one. I can multiply my n, which is 2, because we're in fact of 2 right now, by the x that I finally have a value for. So what is 2 times 1? That's my answer. I'm going to give that back to whoever called me. 2 times 1 is 2. I'm going to return that to fact of 3, the person below me, and my work is done. I'm going to go and shred this piece of paper now. The answer is there. And so fact of 3, again, was waiting on this line for fact of 2 to finish, it can put the answer into its x variable. Boop. So you see how this is working, how it's looping without a loop. Isn't that cool? It's looping using this idea. So fact of 3 was waiting on this. It now has an answer for fact of 2. It can multiply its 3 by its x, by a fact of 2. So it gives back 6, and that's the correct factorial of 3, isn't it? It gives that back to fact of 4, shreds itself. I'm done with my work. Now we're back in fact of 4. That's the topmost thing on our stack of papers to finish. Stack of work. It puts the answer that it got back from fact of 3 into its x variable, so it puts the 6 there. And then it gives back as its answer its n, which is 4, times its x, which is 6, so 24. And that is the correct answer for the factorial of 4, isn't it? And finally, now we're back in fact of 5, the original call to factorial. That's the top of our stack now. It's the topmost paper that has not yet been shredded and been done. So finally, fact of 5 was waiting on fact of 4. It waited all this time. It got back its answer from fact of 4. It returned it to it. It got back 24 to place in its x. And all it needs to do now is run this very last line, and that was what print was waiting on, right? It needs to give back its n, which is 5, times its x, which is 24. And apparently that answer is 120. And now we're back in print, and print can finally print to our screen 120 and call it a day. And now its work is done too. Okay? So that is why we are looping without a loop. This is called a stack diagram, and that's why Factorial is working and doing the thing that it's supposed to do. Are there any questions about that? Because that is one of the most complicated things, I think, in this class, this idea. Any questions about it? All right. I think that's all I have for you then. Yeah, no new assignments. It's too late in the semester for that, but I'll give you this code. Please study it because it's a very interesting topic, I think.